All right, guys, you're almost there. Welcome to session number 7. Session number 7 is going to take 64 minutes, so just a little bit over an hour. And this one is going to be moving towards geology. So it's going to be talking a little bit about some physical geology. So it'll mention rock cycle a little bit. It's going to talk about different structures. It's going to talk about earthquakes a little bit and how to kind of talk about different types of faults. It also is going to talk on the end of it, it's going to touch a little bit on like scientific method. It's going to also talk about a little bit, like it's a little bit random at the end. Some subjects that people have requested when I first did these recordings or first did these sessions. So there's also a little bit about acids and bases. So feel free to skip around if you feel like you don't need the scientific method stuff because you've got that. That's like the last 12-ish minutes. So this session might be a little bit shorter for you if you feel pretty good about that content. You're almost there. You have one more recording to go. And again, happy studying. I actually wanted to use one of the questions that a lot of people had wrong on our last exit ticket, and it's this one right here. An insect lays its eggs on a specific type of plant leaf. The leaves hide the insect from predators and protect them from the environment. As the eggs hatch, the insect larvae feed on the leaves. Which best describes that relationship? I'm gonna give everybody a second to think.
D.
Good. I muted myself. I muted myself by accident. Good. So for some reason on the exit ticket, a lot of people put mutualism, but I'm glad tonight to see more people seeing parasitism because this is definitely that. The host is being harmed in this situation. Therefore, this is a parasitic relationship. Hey, Mr. John.
Hello. Sorry I was a little late. Thank you.
Not a problem. I did tell everybody at the beginning about 20 minutes ago, I sent out the slides for the night with the notes on it. So if anybody does want to kind of follow along or want to look at them later, a lot of the stuff, the talking points for tonight are on those slides. Well, now that we're good here, let's move on to some of our topics for tonight. So the majority of tonight, I'm going to spend talking about physical geology, so some maps, some plate tectonic stuff, and then we'll end up with some historical geology. So we'll talk about a couple of theories that are important, some names that we need, and that is how we will finish up our hour together tonight. So let's dive on into some physical geology. When I took my Praxis, this was probably one of my weaker areas too. I don't ever think I took a geology class. So if you're like me, I'm going to do my best to get this to you. First thing we're going to start talking about is just some of the different types of maps. So the physical geology section of your test is very, very focused on like, do you know what this type of map is and can you pull out some information for it? The first type of map on our screen is a globe. A globe is supposed to be the most accurate representation of our planet. However, it does not show small, minute details, so this is good at seeing large land masses and relative spaces. This next one over is called a Mercator projection. So this is the one, it's got very fine line grids. This is mostly used by marine substances, so this is used by the Navy, and this is what we use to map certain climatological things. So if you ever had like a longitude and latitude map and you're trying to learn different climates and Tropic of Cancer and all that type of stuff, you're probably looking at a Mercator projection. It is pretty good, however, we do have some distortion. So that's why we had our next projection right next to it, which is the Robinson projection. Robinson was created to kind of be like a hybrid between the Mercator and the globe. So this is the one that you've probably seen when you were in school. It's a little bit more distorted at the poles, but it's designed to be a little bit easier to see on the eyes. So that is where Robinson comes from. Down here towards the bottom is probably not one that many of us are familiar with. I know I certainly wasn't when I was studying for this test. but that is a conic projection, and that's used for mapping continental and regional areas. It is very similar to our second to last one, which is a mnemonic projection. However, mnemonic projections are mostly used by seismologists, so people who are trying to study earthquake behavior. It shows you the poles really accurately. The other land masses are relatively distorted, but they're going to use this to predict seismic maps, and if we have an earthquake, it's going to help. That's how they project where the earthquake would hit afterwards. Lastly, we have topographical or contour maps. Most questions on the test are going to be geared towards topographic or global maps. So we're going to spend a little bit of time, just for a quick second, making sure we understand how to read topographical or contour maps. If anybody ends up teaching earth science or 8th grade, I don't know what they call it, if they still call it earth science, they might call it geology, they have many, many standards in CMS on just topographical and contour mapping. So this is going to be a little overlap for what a lot of us will probably have to be teaching next year. So biggest things to know about a topographical map is that first, a my gracious, I'm sorry, everybody, I can't speak today. A topographical map is supposed to be a top-down view of an elevated surface. So if anybody's ever been hiking, you probably use a topographical map to try to figure out like the best route up a mountain, to help you figure out if there's any steep drops and which is the easiest slope to climb. So in this picture, if I was looking at this mountain straight on and I just flip my view to top down, I would end up with this topograph. Each of the lines is called a contour line, and they're spaced out at roughly, these little interval numbers tell you elevations. So no matter what the elevation of the actual mountain is, your topographical contour lines should be spaced at an even interval. So if I were looking at this map and I see this 2,500 on top, that lets me know I have a peak. Another thing to know about the lines is that the farther they are spaced out, the more gradual the slope. So this side over here, where these lines are very close together, this indicates that there's a very steep side here. So if I were going to hike this mountain, I would definitely want to start on the left side where the numbers are farther spaced apart, because that means the slope is relatively easy to climb. Versus this might be a cliff because the topographical lines are very, very close. Questions there? Okay. That's just what I was saying. The other part right here, down here at the bottom, if you ever had a depression or a valley, it would be marked by a circle with some hasher or dashed lines through the center. So instead of seeing, if say this was a crater on the top of this mountain, there would be a bunch of little dashes on the inside to indicate that it is a valley versus a crater. So because we see no hasher lines on any of these circles, I know that these are all slopes for our mountaintop. So if we had to look at a question about a contour map, there would be phrases like this. This question says, which of the following land features is represented at location X? So X is right over here. Would this be a valley, a depression, a cliff, or a hilltop? What do we think? Good. I've got C's in the chats, and I heard the word cliff.
Cliff.
Thanks, Josh. This is definitely a cliff. The lines are very, very close together, so this is a cliff. Bonus question, what would this be? What would this be on our map?
A depression.
Yeah, that would be a depression.
Hey, I know all about maps.
You do? Oh, you do. Yeah. Look, Army man, can you teach this part for me? No? Okay.
I don't think the level of detail is
that
needed. Necessary. Yeah, I don't think it's necessary.
Okay, well, once you get into your classroom, if I ever have to teach about maps again, I'm just gonna be like, oh, we're gonna go find Mr. Josh, guys. Because this is not my specialty in science. But yes, this would be our depression. That would be a valley of some sort, some down into the ground because it's indicated by our hasher marks here. Great, great, great. So moving on from our maps, because again, most of it is about topographical, but when we talk about historical geology, we do also need to talk about this thing, what you probably learned in school. The 4 maps above show the orientation of the Earth's land masses during 4 different periods of time. Which order would you put them in to go from where we started to where we kind of are now? Okay, I hear 4, 2, 3, 1, and I hear 4, 2, 1, 3. What are we thinking? Well, 4, 2, 1, 3. The majority has said 4, 2, 1, 3. And there you go. So the only trick right here, oh, there we go. That's the answer. Don't look at that. The reason we know that 3 is currently where we are is because if you look at this little tail down here for South America, it has separated from what is Antarctica on this little map, whereas in 1, there's still a little bit of a bridge there. So bonus question, anybody know what theory this is, this big guy?
Pangea.
That's Pangea. Second bonus question, anybody knew who came up with the concept of like Pangea and continental drift?
Mr.
Darwin.
Oh, that's good.
Matt, I wish his name was Mr. Pangea, but his name is Wegener, Alfred Wegener. So again, middle school people, they're really, Dr. Pangea, I like that better. Alfred Wegener is the name that we need to know, and he first proposed the continental drift theory in 1912. So he was discredited at first because he didn't have the right evidence to back up his theory. So basically Wegener was like, the continents look like puzzle pieces, so I think they all went together, which we know is actually part of this theory, but because that's what he said, people were like, yeah, okay, bro, I feel like there's got to be more to it. And according to Wegener, like these continents eventually just were located on something, and over time they just drifted apart. Now, thanks to science and our lovely geologists, we know that Wegener was, in fact, correct to some extent. However, the continents didn't just like float on water away from each other. They are located on plates, and those plates have shifted, and that's what has caused the continents to separate into the ones that we know them as today versus Pangea, the supercontinent. So our current theory is known as the plate tectonic theory, which essentially says all of our globe is separated into these giant, massive plates that float around. Now, what are those plates floating on? Anybody know? Magma, exactly. So our Earth is divided into different layers based on physical properties. We live on top of the continental crust, and which is only a couple miles thick, and then right below us is the lithosphere. The lithosphere is broken up into the different plates. So the crust sits on top of the lithosphere. The lithosphere is the plates. That's where the plates are. Those plates float around on the upper mantle, which is composed of magma. Okay. Josh, I don't know the answers to that, but I'm going to find out because now I want to know. One quick thing before we move on to plate tectonic theory. This kind of plays into chemistry as well, but one thing you want to note here is the theory of convection. So all of these, if you've ever looked at a pot of water boiling, you see that the bubbles start on the bottom, they rise to the top, and then come back down again. That is convection. So like they get really hot, they rise to the top, they cool down, they fall back over. So like I like to cook, and sometimes they tell you to get things to a rolling boil, where literally like the bubbles are like coming up and going down. That's how magma works in the core. So the outer core is super hot, the magma moves up to the lower and upper mantle, it cools down, it falls back down, heats up, and keeps going around and around in a cycle. That convection and that constant motion is what moves the plates on the lithosphere. It's the rolling of that magma underneath, kind of like boiling water. So our lithosphere, the layer of the crust that's right beneath the soil that we stand on, is especially important because it gives us the resources that we need in order to do many things. So many of the minerals that we use, that we mine for, our coal and petroleum and our fossil fuels are all found in the lithosphere. Many nutrients from plants that we then need to eat or that we need to breathe, because we do need our plants for oxygen. All of their nutrients and stuff are found in the lithosphere. So if we branch this topic over into like the human impact part of the test, this is another area where they like to ask you questions about like what's going on with fossil fuel. We know that fossil fuels are starting to run out because it takes a long time for things to fossilize. So if we keep stealing all the resources from the fossils and things don't have time to refossilize, we are eventually going to run out of that fossil fuel. One quick kind of like, I want to talk about the minerals real quick. Actually, the difference between a rock and a mineral, because this I did not know particularly well in the geology section, but it does like us to talk about. When we say a mineral, we are talking about naturally occurring inorganic solids that have a crystalline structure. So that means they're usually, the structure of them is in a type of lattice work, and they're usually, like if you ever look at a crystal of salt up close, it looks like a little cube. That's how a lot of our minerals are shaped. So these are things that occurred naturally in the lithosphere. Rocks, however, are actually defined as any solid mass of material or mineral-like matter. So rocks are naturally occurring, but rocks are more like heterogeneous and homogeneous mixtures of minerals, whereas minerals are like pure substances in of themselves. So if I were to mix a bunch of minerals together and make one solid thing, I would have a rock. But we tend to use those terms kind of interchangeably, but it's important to know that minerals and rocks are not the same. Also, speaking about our rocks, one thing they do like to ask you about is the process by which things turn into rocks, or the process by which we get different rocks. Sorry, I forgot this was here. Let's talk about minerals first. I apologize. When we talk about minerals, the one thing that they're going to really ask you about is what test you can use to figure out what mineral is which. There are several different tests, and I've listed 1, 2, 3, the 6 most common. There's about 12 different ways to figure it out. But one thing you can do is look at chemical form. So you can say some crystals take very specific shapes. For example, like I said, salt. Salt is sodium chloride, and it always takes this square block shape. Luster is essentially how shiny something is. So it's the way the mineral reflects light. Hardness is probably the best way to figure out what mineral it is, because we have something called the Mohs scale, M-O-H-S. The Mohs scale has hardness of 10 known minerals. And if you come across something unknown, you can literally try to scratch it and match it up on the Mohs scale to give you a pretty good identity of what it is. The softest thing on the Mohs scale would be talc. I never say the word right, but it literally can be scratched with a fingernail. That would be a 1. And a 10 on the Mohs scale would be a diamond. Can't really, they're very, very hard to damage. Cleavage and fracture is how evenly a mineral breaks and the shapes that it makes when it does break. Streak is like if you took a mineral and dragged it across the ground like a piece of chalk, it would be the color that it leaves behind. And then you also can try to identify some minerals by their colors, but if you look over here and you look at all these different types of quartz, that is not always simple, because some minerals have the same color as others. So for example, like this is quartz, but it looks like amethyst. And you can have quartz, and this is labeled aqua quartz, which is the same color as aquamarine. So color would be the least reliable form of mineral identification. Everybody okay? So when we talk about our rocks, This is the rock cycle. And this is how we create any type of rock that we could have. For those that end up teaching earth science, I have a really, really fun lab, because teaching the rock cycle to kids is not, it's not entertaining at all. They are not a fan of this. However, I do have a lab where you basically take starburst and heat them up and smash them together to make the different types of rocks. So anything that they can eat, they love. So that's a really fun way to teach this if you ever have to. But if we started at the top of our rock cycle, and it's important to note that this is not just a circle. You can skip around it depending on your heat and your pressure. But say we started with a sample of magma that was in our core. When that magma solidifies, it becomes igneous rock. So if you went to Hawaii and you looked at all that nice black obsidian-like substance right on the side of the volcano that is now cooled and hardened, that is igneous rock. Through weathering, erosion, deposition, that igneous rock breaks apart into sediments. And if you add enough heat and pressure, that sediment turns into sedimentary rock. So again, this whole process is driven by heat and pressure. Heat, pressure, and erosion. That's what changes this whole thing. If you have a sedimentary rock and you take it through a metamorphic process, which again is more heat and pressure, you change it into metamorphic rock. And if you add even more heat to metamorphic rock, you've changed it back to magma, and you can start this process all over again. Like I said, if you had an igneous rock and you just heat it up super fast and almost right before you melted, you would change it back to metamorphic rock. So you can skip around the cycle here. Questions on the rock cycle? That was the briefest way that I could tell you it. The key to understanding the rock cycle is that everything is driven by heat and pressure. The more heat and pressure, the more you change your rocks. So let's look at a question. If I had these minerals, which of the following properties would be most useful in distinguishing fluorine from quartz? I see some people saying color. I heard the word hardness. So if we had to go between color and hardness, which would be the best way to identify the two?
Color.
Color.
Remember, think about this one. Hold on, let's go back. Think about this right here. These are all quartz. So it might not be the most helpful to identify quartz by its color because it can be so many different colors.
So hardness?
Hardness. Hardness is the most useful way to identify a mineral. Again, we would use that Mohs scale, M-O-H-S, and that can help us pretty much narrow down within a very small group what our potential minerals would be. Especially if we were trying to distinguish fluorine from quartz, they would both have very different hardnesses on the Mohs scale. And that would be the best way to narrow them down.
So you're saying hardness is the best way to identify
A mineral, yes.
Okay.
One more question. So this one is about rock. The rock sequence of shale to slate, slate to phyllite, phyllite to schist, schist to gneiss illustrates the sequence of what? What do you think this sequence would be? Give you guys a minute to think. Hey, good job, guys. Geology was not my thing, but I'm seeing metamorphism in the chat, and I agree. Metamorphic rock is formed from all different types of rock. So even if you had no idea what any of these different names were, you probably can infer that they're different types of rock. So at the end of the rock cycle was metamorphic, and it's made from any type of rock just kind of smashed together with high heat and pressure. So this is the example of metamorphism. We're changing into a whole bunch of different things. Everybody all right? If you have questions, I got you too. And don't forget, so if I said something too fast, I did email out the slides with a bunch of my notes at the bottom so that you can see a lot of the things that I've been talking about if I'm talking too fast or if you need something repeated.
Shauna, what is lithification?
Lithifications, let me go back here just to show you. Where is lithification? Oh, I didn't put it here, my bad. When you lithify a rock, it is almost the same thing as weathering and erosion.
Oh, okay, okay.
But lithification happens within the crust, whereas weathering happens on top of the crust.
Okay.
Because weathering is usually like wind and water.
Mm-hmm.
Lithification is like other rocks are smashing into one rock.
And that's in the crust itself.
Yes.
Is that right? Okay, great. Thank you.
Yo, no problem. One more question. This one requires you to think a little bit about chemistry, and that should be CaCO3 should be small. But I want to see if we can infer or guess, even if we're not great at chemistry or great at geology, what do you think? And we'll think this one through in just a second. Now, even if you weren't 100% sure of the answer, if we were using process of elimination, what two do we think we could get rid of?
Probably C.
I agree. Why can we eliminate C from our answer choices?
Because they react
Because they're definitely not the same type of rock because they're not reacting the same way.
Right. If these were both the same type of rock, they should probably react together, which is also kind of a reason why you could eliminate D. If they were found together, they're more likely than not composed of the same substance. So C and D are best to eliminate. In the chat, I'm seeing mostly A, and I agree.
that's more like carbonate.
Yep, so one of the most common tests to see if a rock contains calcium carbonate is to use an acid test. So acids react in the form, react when you pair them with a base, I'm sorry, not with a base, with carbonates, CO3. Any carbonate reacts in the presence of an acid. So if I pour some acid on a rock, I know if it has calcium carbonate in it, or carbonated stuff. Now, granted, if you were not sure, using that process of elimination to get C and D out of there already guaranteed that you have a higher chance than not of getting this question correct. Okay. Just a couple other things to talk about in terms of our geology piece. One other thing we want to talk about is something called the asthenosphere. The asthenosphere is also the same name as our upper mantle right here. So as I mentioned before, all of this stuff is going through convection, which means the heat is rising to the top goes back to the bottom. That convection current in the asthenosphere, again, is what's moving all of our lithospheric plates. What happens if lithospheric plates move, guys? There are three things that can, well, more than three, but three major things happen when you move a plate. What happens?
Earthquake.
Earthquake is one. What else could happen?
Volcano.
Volcanoes. Anything else?
Valley or
Mountains or valleys, right? There's more than three, but the three biggest ones we usually think of are earthquakes, volcanoes, and mountain ranges. Valleys and rifts also happen too. So to kind of finish out our physical geology part, let's look at our different plate boundaries. So plate boundaries are where the tectonic plates are coming in contact with another plate. When two plates come in contact, there are three major things that can happen. So the first thing you could have is a convergent boundary where your two plates collide. When the two plates collide, they can't do too much. So usually what's going to happen is something called subduction. So say this plate is lighter than this plate. When these two match, the heavy one is going to be forced underneath the lighter plate, and this is considered to be subduction. So at convergent plate boundaries, one plate will subduct under the other. Now, right here on the slide, I've put what happens when our different types of plates subduct. So if I have two oceanic plates and one subducts beneath the other, I have formed a trench, like the Mariana Trench. If I have an oceanic plate and a continental plate, I can also get a trench, but most likely you're going to get very strong earthquakes. Okay, so not similar to the ones in California. That's a different reason for those earthquakes. But these are like the ones that were happening down towards Indonesia and Asia. There's a continental and an oceanic plate sitting on top of one another, and that's causing some of those earthquakes over there. And then lastly, if you have two continental plates subducting, you end up with mountain ranges. So the top plate is going to be forced upward, and you'll end up with a mountain range. And that's the theory for how the Himalayan mountains were formed. They believe a continental plate hit another continental plate and shot upwards. The next type of plate boundary is the opposite of convergent. So convergent means coming together. This will be divergent, which means the plates are being pulled apart. If plates are pulled apart at a very rapid rate, you get mountain chains. So basically that magma is going to kind of shoot up and create, it's going to shoot up and solidify, which will create very large mountain ranges. However, if you get very slow spreading divergent boundaries, you end up valleys on a ridge crest. So the mid-Atlantic ridge in the ocean is formed by two oceanic plates slowly drifting apart. That magma bubbles up in the ocean, creates a little space, they move apart again, and it keeps happening over and over again. Is anybody in here from California? Good for us. So none of us will fall off and none of our families will. But in California, they're dealing with the transform plate boundary. In a transform plate boundary, you have two plates that are sitting side by side under very high tension, and one of them starts to slip suddenly. So if I had two plates like this, one would give just a little bit because they're trying to slide past each other, and that creates fault lines. So the San Andreas Fault that runs down California, which causes massive earthquakes over there, that's caused by that little transform boundary, one of those places just slipping a little bit and releasing all of the energy that has been pent up. So when we have transform boundaries, there is something, the direction of the transform, the direct direction in which you look at it determines which transform boundary you look at, because you can have a right slip or you can have a left slip, which sounds kind of strange, but I'm going to give you a question so we can see what that looks like. Before I give you that question, which type of boundary is this one? What do we think? Yes, this is transform. They're slipping past one another. Now, which type of transform boundary would this be? This is the harder question, but again, it's based on how you're looking at it. Ooh, screen froze there for a second. I see D. Okay. Sorry for my son, guys. He's having a meltdown up there. So I'm glad to see that nobody says this one's A. Okay. If this were a normal transform fault, that means you would be looking at it head on like this, and you would just literally see like a front and back motion. Most people in the chat said D, and I agree. So In the left strike slip fault, the side appears to be displaced to the left. That means it's kind of tilting towards the left in comparison to where you are as the viewer. So if you were looking at this straight on, it would be displaced to your left, making this a left lateral strike slip. So it literally is based on where are you viewing this fault from. If the arrows were tilted a little bit more to the right, then this would be a right lateral strike slip. If it were reversed, then literally those two arrows, one facing, the arrows would be switched in terms of their direction. Again, normal means you're looking at it straight on. Left means it's tilted to your left. Right means it's tilted to your right. How are we doing?
How would a reverse look if you were looking at it straight on? Is that the way to look at that?
If this were straight on, then the left side would be going away from you.
I see. Okay.
So if this were straight on and the left side were coming towards me, then it would be a normal a normal strike slip. But
Okay.
if I was looking at it straight on and the left side were now away from me, it would be reversed.
Great. Thanks. That makes sense. Okay.
All right. So just a little bit about historical geology, because it's already 7:40 and I do want to respect everybody's time. What is this? It's the Grand Canyon. Does anybody know why the Grand Canyon looks like this? It's pretty. Part of it is sedimentary rock. Part of it has been due to weathering and erosion. They think that at one point in time, there was water that flowed through some of these that changed up the patterns. The coolest thing about the Grand Canyon is that it's literally a gigantic piece of history. It's like a big old storybook of what used to happen. And if you have a trained eye, you can figure out what used to be where and what mountaintop may have fell down based on just the sedimentary rock and the colors and the weathering and the erosion. So this is where historical geology kind of comes into place. And we're going to talk about a couple ways that they kind of figure out what goes where in terms of our weathering and erosion and how they figured out the age of things in the Grand Canyon. First way they did it was through techniques under the relative age dating category. So when we look at the Grand Canyon, scientists are able to kind of give not an accurate date. So they can't say this happened 100,000 years ago, but they're able to kind of see the sequence of events. So using things like original horizontality, which means sedimentary rocks are all deposited in horizontal straight layers. So if you think about like the beach, rock is deposited flat. When more rock comes, everything is like, oh, best way to think about this. Did anybody ever make sand scopes? The little things where you pour the sand, the colored sand in the thing and it layers up on itself? And they form like, so if I poured a bunch of colored sand in a tube, you would just get layer upon layer upon layer. All of that sand would be deposited straight, which is original horizontality. And as I keep adding layers, it would just keep piling on. That also ties into this thing called superposition, which says undisturbed rocks are at the bottom. So if I have a whole column of rocks that has never really been bothered, the oldest ones would be at the bottom and the sediment just kept piling on top of that rock. Piling on top. So the newest rock is at the top and the oldest rock is at the bottom. So that means if we're looking at pieces of the Grand Canyon, things down here at the bottom of the canyon are super, super old. And everything else, all these horizontal red stripes have been piling on top of the older rock. So the higher you have to go, the newer that you are. When you have an intrusion, so an intrusion is a piece of rock that has kind of been stuck into another piece of rock. So you could have like a cliff fell into it and like the rock is being deposited around it. Intrusions are younger than the rock that cuts across it. So that means anything that fell into an undisturbed sequence is younger than the structure that was already there.
Okay.
A couple other things, you have inclusions. That's just fragments of rock layer must be older than the rock layer that contains them. So that means like if I had some limestone and it kind of got submerged in a piece of calcium, the limestone would be older than calcium. The limestone had to be formed before the calcium could grow around it. So that would be an inclusion. Unconformities, so rock immediately above an unconformity is younger than rock immediately below it. Unconformities just means something looks different. Something's wrong here. So when you look back at our Grand Canyon, like you see these yellow spots where everything else is red sedimentary rock, that could be an unconformity. Something is a little bit different. It's not conforming to the rest of the substances that are around it. So when we think about relative dating, I would know that that yellow area is younger than the rest of the rock that surrounds it. One of the big pieces that they're going to ask you questions on is this thing called correlation, which kind of ties back into Pangea. But essentially what they say is if you have two mountain peaks and say the top of one mountain matches the rock that's at the bottom of another mountain, I can kind of put together the pieces to figure out who's older than who. That's usually done by fossils or radioactive dating, which we'll talk about in just a second. So to make this last piece make sense, I'm going to use a question that's popped up a bunch of times in a bunch of different practice tests, and it's here. So for this one, think about that concept of correlation. It says the figure shown are rock columns from two different canyons on the Colorado Plateau. Of the following, which layer would be the oldest? So you have option A, which is the Coconino sandstone. B would be the Carmel sandstone. C would be the Chinle Formation. And D would be the Kaibab Formation. I want to give everyone to take a minute to think. I see one answer already, but we'll take a minute to think real quick. Okay, so I see A's and I see D's. So for everybody that says D, I want to point out one thing to you. So according to the law of superposition, yes, right here, the Kaibab Formation would be the oldest in B. But think about that piece about correlation. Do you see the Kaibab Formation in the other side, in the Grand Canyon?
Oh, yeah, it's on the top.
Yep. Kaibab is the top of the Grand Canyon. So if we think about correlation, if it's the bottom of Zion, but the top of Kaibab, that means Zion has to be what? Younger or older than Grand Canyon?
Younger.
Younger. So that means all of the rock on this side would be older than all of the rocks on this side. So the answer is actually A.
A.
Mm-hmm.
Mhm.
So we're supposed to be like the top of Grand Canyon basically fell and started Zion Canyon
Exactly.
growth. Okay.
So this is where they like to kind of get you, because if everybody who said D was thinking correctly about superposition. Oldest is on the bottom. But they like to play on the fact that there are sometimes lesser known concepts to this, like correlation, which can kind of get us a little bit. But good catch there, everybody. I wanted to talk briefly about some absolute age dating. So there's three major techniques. If you were not here at the beginning sessions, we did half-life in chemistry, so that'll come back around in a session or two for the people who weren't in the beginning. But one of the three ways we can do absolute age dating, which means we can pinpoint the age down to a couple hundred years, give or take. First is radioactive decay. So they look for which particles are remaining. So if we have alpha particles being taken out, beta particles, and we see how much of that isotope is left. Half-life is the amount of time it takes for 1/2 of an isotope to be cut in half. So we can look for certain amounts of radioactive isotopes in some rock and see how much is left and determine the half-life from there, and that can help us tell how long something has been around. And then the last one is the most useful in terms of age dating of rocks, and that's radiocarbon dating. So this isotope is carbon-14 in his bag. Carbon-14 has a half-life of 5,730 years. So that means every 5,730 years, carbon-14, the presence of it should be less and less and less. So if we are looking at a sample of rock and it's got, I don't know, say 1 full gram of carbon-14, I can say that it's been around for about 5,730 years. However, if it only had 1/2 gram of carbon-14, I could say it's been around for about 11,000 years, based just on the presence of carbon-14 and knowing its half-life. I only know the half-life of carbon-14 because I'm teaching my chemistry students half-life decay, and we talked about the number 47 times today. Anybody have preguntas on this part? Sorry, y'all. So speaking of some radioactivity things, this question does not even really require you to know anything about radioactivity other than what we've kind of talked about. A radioactive source is monitored for 1 minute at hourly intervals by the use of a Geiger counter, yielding the data in the chart over here. So even if you don't know half-life, even if you have no idea what I was talking about in terms of radiocarbon dating, this one is actually phrased as a radioactive question, but it's really asking you just to analyze the data and figure out what would be inconsistent with what is happening here. So according to this information, where we have an increase in time and we've got something going on with the observed counts per minute, which of the following statements would be inconsistent with that data? And for my analytical people, don't overthink this one. So in the chats, I'm seeing mostly B's and D's. So let's start our narrowing down there, because I agree that it's not A, because there's not too many fluctuations in the data. I also agree that C is probably true because the time is increasing by 1 hour. B says that doubling the observation times to 2 minutes will approximately double the number of counts recorded. And D says the count rate will increase in the coming hours. Excuse me. I see some people switching their answers to D. Can anybody tell me why this would be D over B?
Because as time goes on with the half-life, the number gets smaller.
Mm-hmm. And what you just said is actually the definition of half-life. At each time interval, the amount should be roughly cut in half. So there are a couple times where it's not 100% half, it might be 51%, 54%, but it would be highly unlikely that this 13 is going to start to all of a sudden increase at the 5th hour. So the only answer that would be inconsistent would be D. The count rate is not likely to increase as time continues to go by. So again, for that one, you don't even really need to know half-life. We just have to pay attention to what our numbers are. More minutes, and I'm going to jump to a little activity for us to do together just to make sure, because again, middle school people, this is to help high school people out too, but middle school needs more names than high school does. So these are some scientists we had about, some that we have not, and all I want to do with our last couple minutes is help us narrow down who did what. So it's always good to know what scientists contributed to scientific discoveries and inquiries. Some of these people can be more than once, and some of them may surprise you. Okay. So what about Marie Curie? Anybody know what she is most responsible for?
Something with the radioactivity.
I agree. Yeah, radioactivity. Yes.
Also, would it be Nobel Prize winner?
Yep. So that one's going to come up at the end, but Marie Curie is one of our 2 Nobel Prize winners on this list. She and her husband actually discovered plutonium, which is the most dangerous radioactive element. So yay and nay for them on that one. What about our friend Mendel?
Something biology.
Genetics.
Genetics.
Excellent. Mendel is our genetics guy. That's the one who gave us the laws of inheritance. So he's the pea plant man.
Yeah.
And so Mendeleev is a little different. Okay.
Periodic table.
Yeah. Moving on to Darwin. Most people know that that's our evolution and natural selection friend.
Yes.
Don't believe the test asks too much about evolutionary tactics, but it's good to know his name. Sometimes they bring up the birds in the Galapagos and they're talking about Darwin, so it's good to know him. Our good old friend Newton, that's Newton's laws and universal gravitation. So if you weren't with me, we do go through Newton's laws a little bit. Oh, there we go. I was looking at time, that's why I started clicking. Galileo is our friend for astronomy and telescopy. So Galileo has a ton of credits to his name. He's responsible for a lot. But in terms of the test, you most likely want to associate him with astronomy and telescopy. What about Hutton? That's a name that a lot of people may not know.
Atomic theory? No.
I'm gonna take a guess and go with color blindness.
Nope. He's actually has to do with what we were just talking about
Radioactivity.
before that.
Theory of relativity? I don't know. Plate.
Geology.
Theory of
Geology.
Geology. That's our geology guy.
geology.
One of the reasons that we got our plate tectonic theory, so Hutton came up with something called the theory of uniformitality or uniformitarianism. That's his word. Sorry. And so what he basically said was, so he was literally standing on a beach and looking at the waves. And he was like, you know what? These waves have been doing this since the beginning of time. So he said that there's certain processes, geologically speaking, that have just been happening since the dawn of time. They never changed. And that's how we can kind of predict that the earth has been doing things. So we know that the waves have always been crashing, but they've never been crashing. So that means continents had to move for things to happen the way they are. So Hutton is one of the first people to kind of help with our current plate tectonic theory. Next up here is one of my favorite people, since I'm a chemistry lady. That's my good old friend Mendeleev, who is our modern organizer of the periodic table. He is the reason why we keep our periodic table as it is. Okay, so he's the one who's like, we have to keep it this shape, which is why when we add new elements, we either add them to the F block down there at the bottom, or some periodic tables have some spaces down on the right, up the right corner that are like empty boxes for elements that have yet to be discovered. What about our friend Einstein?
MC squared.
Yep. He has another one on here too.
Measurement.
Theory of relativity.
Theory of relativity.
Yes.
For every
Einstein.
action, there's a reaction.
That's new, and relativity is similar though. So same concept.
Okay.
Dalton is another one of my friends because he's a chemistry guy. And he is atomic theory and color blindness. So we know color blindness is a sex-linked trait. Dalton, the other name for color blindness is actually called Daltonism. So he was one of the first people to do some research into why people are colorblind. So that's one that a lot of people don't know about Dalton, but there we go. Now we've got a couple people on here whose name are also a unit of measurement. Anybody know who?
Newton.
A Newton is a unit of measurement for force. So when we talk about force equals mass times acceleration, you can say that things fall with a certain Newton. So Newton is a unit of measurement. And also we have a Dalton, which is a unit of measurement in chemistry that is not widely used, but it's there. And we've already mentioned our Nobel Prize winners, but that would be Marie Curie and Einstein. So our time is 7:29. So we made excellent time today. I'm sorry for talking y'all ears off this evening. Do y'all mind if I do one more problem with you? Just one more thing I want to make sure that we understand, because these questions can pop up in the very beginning of the test or the very end of your test. So the beginning of your test is called like scientific theory, blah, 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 lab techniques. That's really just the scientific method and do you know not to blow stuff up in a lab? That's what it's about.
I'm sorry.
So some people say they got, being honest, sorry, Miss Simmons. One question that people said they got was like, should you pipette things with your mouth? And like clearly the answer is like, should you wear gloves in the lab? Clearly the answer is yes. And I say clearly, even though one of my coworkers burned her hand on acid today because she wasn't wearing gloves. But, not gonna talk about it. But one of the things I want to make sure I point out is our experimental design, so scientific method, which most of us have probably heard about. But I want to make sure that we know the difference between our independent, dependent, and control variables, because sometimes this is what we get a little switched up on. So remember, in any good experimental design, you should have an independent variable. And I don't think they're going to ask you about creationism on a real test because it's kind of controversial. Sorry, guys. I see the chat questions and response, so I don't forget, just so y'all know. Yeah, I don't think they will ask you about creationism, only because everybody takes these tests and Bible Belt states tend to stay away from questions about evolution and creationism. So I'm gonna bet on no on that one, but please let me know if it pops up. Okay. So in an experimental design, independent variables are what you change. So in a good experimental design, you want one independent variable. You only want to change one thing so you can ensure that you are causing your change where you want to. Dependent variables are what you observe, okay? And also in any good experimental design, you should have a control, and that's what you use to compare to. So another question you might encounter on your Praxis is something like this, where they just want you to read these and keep in your mind independent, dependent variable. So it says the onset of stomach ulcers and gastroesophageal reflux disease have been directly linked to stomach hyperacidity in some cases. Data collected from the experiment measuring the effect of 3 new drugs, X, Y, and Z, is shown. What would the dependent variable be in this experiment?
So it's being changed.
Then, good, Justine.
Time of stomach pH.
I was thinking D. Well,
so various drugs tested are what you change, so that would be independent.
Okay.
But when you just look at kind of like the X and the Y to kind of eliminate some stuff too. Okay.
But also think, so dependent is what you're looking to change. What do you want these drugs to affect? You want them to change stomach pH. You want them to make your stomach less acidic. So the dependent variable in this one would be C. Now, if you've noticed, some of the questions for the Praxis have you tie in multiple areas at once. So this next question is going to have you think about some chemistry for a quick second. So it says treatment from which of the following, I'll go back in 1 second, Ms. Simmons, I got you. It says treatment with which of the following was the most effective in reducing stomach acid. So for this one, you have to understand pH scale just a little bit.
7 is neutral.
That's what I was thinking.
Ah.
I was thinking A.
Make sure I look at mine.
Can you enlarge that, please?
Yeah, I know. I can barely see it. So
Okay, let me try. Hold on. It's a little hard. Hold on 1 second. Sorry, y'all. Google Slides. Get a little.
Saline and.
I'm going with C.
Going with C?
Yeah.
Okay, I'm gonna enlarge this one more time. Let me see if I can make it bigger for you.
triangle. It's hard to see.
Let's see if this is better.
Okay, thank you. So saline is the circle thing. No, that ain't gonna work. So
Yeah, so C.
it's gotta be C.
Yeah, C was drug Y, right?
Oh,
Yeah, because it lowering the
Yeah.
stomach acidity would raise the pH, which would make it more basic.
Mm-hmm.
Can you say that one more time? I didn't hear that.
So let
I
me
said
put this
so.
up. Go ahead.
Yeah, so lowering the pH would actually raise it. So it would make your stomach more basic. So if you lose acid, you would go closer to 14 and away from 0.
Wait, so you saying you want to be more basic than acidic?
Mm-hmm.
Yeah, because if you got less acid in your stomach, then there's less acidity in your stomach. So the pH would rise instead of fall.
Correct.
So if you look at this image right here, it's telling you that normal stomach acid is about a 1 on the pH scale, which means it's super corrosive. The farther you get to the sides of the pH scale, the stronger you are.
Mm-hmm.
So 7 right here is neutral. So like pure, fresh H2O would be a neutral substance. It's neither acidic nor basic. If you have acid problems, so if you have like reflux, that means the stomach, your acidity in your stomach is far too strong for your esophagus and everything to handle. So that's why we take antacids. And acids are basically right here on the pH scales. They're like 9 or 10. They're bases. When you mix an acid and a base together, they should hopefully neutralize and bring you closer to 7. So when we look back at this drug, you want to see which one gets you closest to 7 or neutral on the pH scale, and that would be drug Y. That means it's the most effective at fixing the pH problem.
So would that mean that saline is kind of like you have a basic stomach per se? Or a basic?
Yeah. So the saline would actually be your control.
Okay.
That would be your control variable because it's keeping you neutral on the baseline scale. Remember, the pH of stomach acid is about a 1 or a 2 anyway, so the saline is showing you that it's not having any effect.
Question.
Yes, ma'am.
Couldn't it also be? It's like neck and neck with X and Y.
So when you look at X, you can see that over time, so X did work effectively in the first couple hours, but then it has a slow decrease, so it does not work anymore.
Okay, gotcha.
Whereas Y, doesn't pick up quite as fast, but it's got a longer longevity for the stomach.
Okay, got it.
It's probably an extended release drug.
Yeah.
Justine, I think I heard you.
Looking at the graph itself, you even need to know any of that stuff because just looking at the graph, you can see that it's the one, like the right one. Just by looking. Not knowing any of that stuff, you can kind of tell, right?
Yeah. So it doesn't necessarily mean you have to know like acids and bases, but it can help to have that little bit of knowledge, just knowing that like 7 is neutral. So that's why this one will work for, but it's playing on both of your skills. So a lot of the, I'm sorry, Justine. And the last thing I wanted to show you guys down here at the bottom is also this tip about acids. Please remember, and this comes up in lab safety, that you never add acid to water. You have to add water to acid. Okay. So you can never, yeah. In lab safety, if you have a substance, so if you're doing a lab and it involves acid and water, you can never add the water to the acid. You have to add the acid to the water first.
So you pour the acid into the water?
Yes, never the water in the acid.
So
in a chemical formula for acids have a high concentration of hydronium, which is just an extra hydrogen. And we know the chemical formula for water is H2O. So if you put water in acid, which already has a really high hydronium concentration, you end up with this massive reaction that can bubble over, cause acid burns, do a whole bunch of crazy things. But if you add the acid to the water and you do it slowly, you minimize the chance of having too much hydronium and you'll have a lesser reaction.
So think about like cleaning supplies, how you don't